Hello, everyone. My name is Isaac Tupac. I am from Jicamarca Radio Observatory, and today I will talk about synchronization between a vertical incident pulse ionospheric radar and an ionospheric echo receiver version 1. So, in this presentation, I will talk about how we got synchronization between a vertical incident pulse ionospheric radar, known as VIPIR, and an ionospheric radar receiver, version 1, mainly composed by a USRP N200. We will see three ways of synchronization to understand the behavior developed in the acquisition. We will also see how the synchronization could affect the obtained ionospheric profile and how the using of OOT blocks and tags could affect the synchronization. Well, the first method is known direct synchronization. We see here VIPIR. VIPIR is an external radar bought by Higamarkanet Observatory to obtain uh, ionograms. We here see the different stage composed by VIPIR. We see the transmission stage, the channels, the front end from the receiver. We see the computer acquisitions. Also, VIPIR uses a logarithmic antenna for transmission and dipoles for reception. We are using for desynchronization a USRP N200, and well, the idea is how will we synchronize? How will we recognize the time to start to receive the echo? So to know the exact time to receive in the USRP, we will have to know the exact time VIPIR will send the echo, the signal. We have to know in which time VIPIR will start the transmission. So for that, uh, Gigamarca have developed a synchronized circuit. This synchronized circuit uses the serial interface signal, the PPS, and the clock on the GPS firmware. Also, it uses a Raspberry, which sends the packets which define the exact time. When I say exact time, it's hour, minute, and second. So at a specific time, this synchronized circuit will generate a pulse. This pulse will go to VIPIR to start that transmission, and we go to the USRP to recognize that the transmission was developed or was initiated, so that the USRP can start the reception. And from the front end, we'll receive the echoes directly to the USRP. We are using GNU Radio 3.8 to create a flow graph. In this flow graph, we could see the Python snip block, and we're using an auto block, the known message truth, GRO4. This auto block, we will change the frequencies for the processing the modulation. We have implemented that in a second thread. So this is doing in an asynchronized way. So if we see the part of synchronization, we will see that the main idea is wait from that for that pulse. So we will create a while that we wait until the pulse is generated, and when it's generated, we will set the USRP register time at 0 at and we will start the acquisition 160 milliseconds after the pulse receiver. So what we got was that the reference level, the transmission reference level was at 0, and also we could see profiles, profile ionospheric, ionospheric profile. So we could see that with this direct synchronization, we could do it well. Then for the second synchronization, uh, I call it a direct synchronization method. Now we also have VIPIR here, the USRP N200, and we are using a GPSDO in this case. Why are we using GPSDO? Because we want this USRP will be far from the transmission. We want to prove a new way of acquisition, so we are using this GPSDO. We are also using the circuit, the synchronizer circuit only for transmission. This will this circuit will also generate a pulse, and we will know in which exact time the transmission started. And the GPSDO, we will ask for the GPS time, and if we are after that time, we will begin the reception. This is the first idea that we had to synchronize this this proposed design. We are also using the same idea, Python snip and message strophe, basically to make the modulation stage. And if we see the Python snip block, inside we see that we ask for the GPS time. As we know the exact time of the transmission, we ask if we are before that time, we will wait. But if we are after that time, we will start the reception because we know that the transmission had already started. When we did that, we see that we had a problem that the sample acquired with the time, with the transmission time, got before the beginning of the acquisition. So GNU Radio showed a mistake. So what we did was add time. So we will wait until the transmission starts, but we will begin the reception 160 milliseconds after the transmission, after we recognize the pulse. But as this block is asynchronous, because we are using polymorphic data type, and we are using a second thread, we have to add frequencies because 160 milliseconds is not, this block will not wait that time. So we will start before. And to be synchronizing frequencies, we have to add that amount of frequencies. In this case, will be 16 frequencies. What we got was that we could see the reference level, but we didn't see it at zero level. Also, we didn't see it a very good profile of metadata of ionospheric echoes. And also we didn't see a good height, as I said. Next, we have to add more time, in this case, 120 milliseconds. And what we saw was that we were closer to the reference. We will a better echo, but it was not so good. What does it mean? It means that transmission and the reception is not at the same time, even when we thought that was correct. We had to add more time. In this case, 480 milliseconds. In the other occasion, say 600 for 640 milliseconds, 800, and with the time 960 milliseconds, we saw that the transmission and the reception started at the same time. This means that VIPIR received the pulse for the transmission, but it took 960 milliseconds to send the signal, the transmission signal. So this is the first observation here. The second observation was that we were not at the correct height. It means at zero level. So what we did was turn off the USRP and restart all the process of the transmission and acquisition, but we only see that the reference level change in position. So this way of synchronization implemented, it was not correct. But we discovered the 160 millisecond introduced for VIPIR as a delay. So as we was not correct, we implemented a third type of synchronization. It's known the PPS method. This is the flow graph that we have used, but in this opportunity, we have not using message passing. We are using tag. What is the idea of tag? So when we recognize the tag, we can change to the other frequency. So we recognize the second tag, we change to the third frequency, and until the end, that in this case will be 1,808 frequencies. So for recognize that tags, we created another auto blocks known count tags, which, as I said, recognize the tag to change the frequencies. Now, how is implemented the Python snip block? There is here the code. First, we have to recognize the GPS time given for the GPSDO. Then we set that time to the registers of the USRP. Then, with that time, we found the epoch in second. With the time epoch in second, we separate the parts of the time. That means the year, the month, the day, the hour, the minute, and the second. The UTC in terms of UTC time. Then to set the start time receptions, we have to set that time in local time. So how we did that? We got the same year, we got the same month, but in this part of the country, we are 5 hours before the UTC hour. So we had to rest 5 hours. Then we started all the process, all this Python flow graph, 1 minute before the recognizing of pulse. For example, if the pulse, if the transmission pulse is started at 1 hour, 2 minutes, and 4 seconds, we will define an hour 1 minute before. So will be 1 hour, 1 minute, and 4 seconds. So that GNU Radio could wait until that time. And after that, we define that time in epoch time, and then we set that time 960 milliseconds, because there is a delay, delay introduced by VIPIR. At that time, we will start the reception of the USRP. In this way, we have developed a correct synchronization that we see here. This is what we got. As we see, we got a good profile. Also, we got the reference at level 0, but if we see the modulation, we see that the change of frequency is not at the same level. It recognized the tags, but the change made it different in different times. And also the tag should be in the middle of the graphic, but it's not in the middle. It's not in the correct height. So we could synchronize correctly, but in terms of the modulation, it's not the better way to obtain ionograms. Conclusions. We could make direct synchronization making the USRP N200, which could recognize one external pulse generated at a specific time. In the indirect synchronization time method, which is the second method, if we only consider the time given from the GPSDO to start the authorization and we don't set the register of the USRP N200, we obtain bad ionograms. We didn't got the reference levels at zero. We had to add frequencies values because the first OLT block created was asynchronized. In the indirect synchronization PPS method, that is the third synchronization, we set the GPSDO time to the USRP register, which was the correct way to synchronize. We created a new OOT block, the last one, which recognized the tag, but as we saw in the ionograms, the modulation was not the better because its tags are only asynchronized, so it's not recommended. We have some reference here about polymorphic type and synchronizations. Tag, also tag. And if you want to contact me or write me, this is my email if you have another question about this subject. This is all. Thank you.
Yes, thank you for your presentation. Is this project related to the ARP project in Alaska? You know, the HAARP, which is dedicated to ionospheric analysis?
I read a paper of UHAC that it had make a receiver also. I'm not sure if it's at university, but he's using USRP to transmit and USRP to receive. We are using here one radar that is bought for an American company, and we are trying to receive echoes from that transmission. So the idea here is to make a net of receiver. So the idea is to put 4 receivers through Peru, and the transmission will start in Lima. So the receivers will be, for example, 100 kilometers far away or 400 kilometers far away. So the problem was that the synchronization, and so what I made in the presentation is the synchronization that we are taking to could receive that echoes from the ionosphere.
Okay, and what is the coverage of the frequency coverage, the band?
It's a range of frequency from 1 megahertz to 15 megahertz now.
15.
There are depends of the experiment. For example, for this experiment, there were 1,808 frequencies. So we have to create that frequencies in GNU Radio. Each frequency was created in 10 milliseconds. So the APP was 10 milliseconds.